Okay, so let's let x1, x2, and so forth up to xn be IID, that's short for independent and identically distributed normal random variables, each with mu and variance, mu for mean and variance sigma squared. Then if I standardize each one of these, right, then I square each one of those standardized normals and sum those squares. Well, this is just a shorter way to write that. This thing turns out behaves like a chi-squared distribution with n degrees of freedom. Okay, we've already talked about that, and this, it turns out, has some really important statistical implications, and so we'll get right to that theorem. Let's again let these x's be independent normals, each where they all come from the same normal distribution, having mean, mu, and variance sigma squared. Then, if I take, first of all, this s, this is a random variable here. S is the sample variance, okay? And I'll just define it right here. I hope this is okay. It turns out that maybe I'll do it like this, okay? So S squared is the sample variance. We have a population variance, which is sigma squared. The sample variance is sort of the, well, it's a variance calculation that you get by looking at your data or by looking at your sample. And it's supposed to be a good estimate for this, okay? Because it turns out in practice when you're doing statistics, you don't usually, you maybe even never know the actual population variance. So you use the sample variance to approximate it. But I'll just define it here. I hope that's okay. It's just it's sort of a weighted average of the squared deviations from the mean, or from the sample mean, really, rather. Okay. So it's a lot like the equation for the population variance, except for a couple of things. Of course, you're subtracting the sample mean from each observation, and then instead of dividing by n, you're dividing by n minus 1. And there's a technical reason for that. It turns out it makes this s squared sort of a better estimator for sigma squared in a sense, because on the average it means that it will be exactly sigma squared on the average. So again, this is how s squared is defined. Okay. All right. Well, so what this theorem really says, though, it doesn't just define. It doesn't. We're not just defining s squared here, but it turns out that this whole quantity, this whole thing, behaves like a chi-square distribution with n minus 1 degrees of freedom. In addition, the sample mean and sample variance are independent. Now, the first time I heard that, I was sort of blown away. That was not obvious to me at all. But then maybe once you see the proof, or once you actually give this a little bit of thought, maybe it does make a little bit of sense that the sample mean and the sample variance are independent. And also, by the way, if you put a subscriptive n on the sample mean, maybe we ought to put it there too. I don't know, just food for thought. All right, I'm not going to prove this. This is proven in all generality in a mathematical statistics class. I'm sure you can find proofs in your book or online anyway, so we'll just go with an example.